Good evening, everyone. Welcome. Thank you for joining us on our dSPACE webinar on SIL or HIL, where you should start. It's great having you all over here, and we had some great response and also a lot of interaction that we had before the webinar started from a lot of participants. Introduce myself, I'm Surya. I will be your host for today's webinar. And before we can get started, I would like to introduce our primary presenters for the day. I have with us Swati Dhanarajachar, who is our expert in all things SIL, and we have Mr. Lal Krishna as well with us. Thank you guys for joining today. Uh, so to set the context for today's webinar, uh, India has today become one of the world's most vibrant mobility ecosystems, uh, be it on the EV side, two-wheeler side, on the commercial side. Uh, Merely months ago, in September, India sold over 2.16 million two-wheelers in a single month, and that's a reminder of how mobility is deeply woven into our everyday life. The two-wheeler market is projected to about 28.8 billion in 2025 to over 37 billion in 2030 in just 3 years. On the commercial side, we are already standing at about $5 billion and is expected to go up to $38.6 billion by 2033. And across the EV world, the last financial year 24-25 closed with over 2 million EVs being sold, making for about 7.8% of all automobile sales in the year. All this tells us one primary thing, and that is that we are not trying to scale. This is momentum. We are building momentum to a mobility world in India. And what that tells us is that India is not just adopting the future of mobility, it's also accelerating it, and it is the primary driver for that. And with that driving comes a lot of complexity. Today, vehicles rely a lot more on electronics, cloud works, and intelligent validation than just mechanical parts and engines. And this is where the software-defined vehicle comes in, why simulation, why SIL, and other elements are more important today than ever before. On that context, I would like to call upon our speaker, Swati, to welcome you all to the rest of the agenda and enlighten us with her topic today. Swati, on to you.
Yeah, thank you, Surya. So I'll just present my screen. Yeah, thank you, Surya. So, hello everyone. Thanks for joining the session. I'm Swati Dhanurajachar, currently working as a field application engineer at dSPACE India. So, my work mainly revolves around software in loop simulation, and I have been working with the tools like Target Link, System Disk, VIOS from past few years. I also have some experience with the compliances like AutoSAR and architectures like AutoSAR concepts and etc. So, yeah, that we have joined the session. We will look into what would be the session. We will dive deep into the session, like everywhere once the testing started or once you have an application, it always has this discussion where you should start. Is it a SIL or is it a HIL? So, yeah, this is where our webinar comes in, and we can break down and see how we can differentiate your test and strategies. Today's agenda flows like with the evaluation of evolution of ECUs and its impact. What are the test strategies that has been defined for this approach, and what are the difference, the roles and definitions of SIL HIL, and how we can segregate the framework for ECU testing. Also, we can see how SIL is complementing HIL. DSpace helps you in that. Also, a small demo on the use case. Also, a case studies from Stellantis and the key takeaways. Yeah, before we dive into the SIL or the HIL discussion, we'll take a moment to understand how we arrived to this point. So basically, electronic units or electronic control units, way before when the automobile or car was introduced, it was more mechanical. We could say there was no electronics at all. As and when the sophistication for the increased, and then the electronics came into picture. So now in 1950s or so, the electronics came into picture, but where it was very minimum, like it was only for fuel injection or engine management or so. But nowadays, the software or the sophistication required or the feature required in the car has been increased. And there, the complexity or the ECUs in a car is very high. Or nowadays, we can see about 70 to 80 ECUs are 70 to 100 ECUs for that case are running in a car. So how are we validating? So now then, it is there. How are we managing it before we go into validation? How are we managing it? So now then we came up with a gateway or a or a functional control or a domain control where we try to segregate the ECUs among different domains, handle the communications in a different levels. But it is not sufficient. Now, as and when the ECU or the software complexity is increasing, now we are moving to centralize the processing in it. That means the not shift. We are now moving all the processing to a central part and to have a minimal control with the zonal ECUs. And there we have reached the SDV. Now, with this, what we foresee is that the complexity of the software is increasing in a sense. We have, with this increasing, we are getting more number of feature. Yes, we have it. So we are going for a more sophisticated lifestyle. Yes, we are going it, but it comes along with the issues, like we have to maintain the safety checks there, safety checks, how what are the faults that are coming in. The complexity brings in the faults or brings in the increase of time, everything. If you are like, it comes in with all the pros and cons along with it. So now it also, when we are detecting these faults at the latest stage, it will cost, it will have increased cost, increased time, and increased risk. So this pushes us towards the continuous improvement, wherein we can go for a rigorous testing in a virtual environment and reduce the dependency on the physical hardware. Also, we can see the front loading of and the left shift of the uh, validation part. So with this, we say that we are going with a test driven approach or test driven development. And how is it so? Let us break down and see a bit. So initially, the application started or the requirement started, the design is finalized, application is developed, middleware is integrated, and the software is integrated to hardware. And now we start the testing. Suppose if at all there is a bug which is encountered in an application, so from again the cycle repeats. Any issue found here, go with the application development, integrate it, integrate it with the hardware, and go for the test. This induces lot of cost and lot of time and effort into it. So then we try to split it. We go for a quality gates or a quality check in between. Application development, we have a quality check with the SIL and with the virtual ECUs for both AutoSAR and non-AutoSAR based. And again, we integrated with the middleware and go for the quality check again, and then go for the real step. What if it is not looped properly? If you are not fixing the bug at, you have a quality check. If you don't do it or if you don't utilize it, again, you will end up with the cycle that comes in. So again, all the cycle has to be conquered. So now with the integration, that is how we are trying to develop. Now we are trying to test thoroughly at the each level, like application develop, test it thoroughly, middleware integration, test it thoroughly, software integration testing, test it thoroughly. How we could do that? So with the, like we are saying, we have to test it. Yes, we can test it. What is the approach that we are integrating or taking it up for? So with the virtual validation or with the ECU development, it is the V cycle that we develop. So we are still using it for the development cycle, but how if we include or we combine it with the agile methodology. So once the application is developed, test it thoroughly, rigorously test it. Once the middleware integration happened, test it thoroughly. So like this, when we combine the modern methodology along with the ECU development with the best strategical test approach, we can achieve a quality product at the end. So with that, Assam have come up with a test strategy with the V cycle, which gives you a detailed strategical approach, which says which type or which method of test or which kind of test that could be done in different environment, right from the model in loop until the open road test field monitoring. Here, nowhere we are saying we are skipping any level of testing. We are saying please approach this test in a strategical way. So now we are saying that there are, like, if we consider the software in loop and hardware in loop in consideration, let us take an example of interface testing. What are the tests that you could completely test or finish your testing at the software in loop level, and what are the tests that you could do or keep it for the hardware in loop level? So now if there are two software components or two software or two ECUs in a software level, and you want to integrate it, only the software functionality or software integration, you can completely do all those checks in the software in loop simulation. Whereas when you go for the hardware in loop simulation, you can check or go for the testing which with respect to the integration between the software and the hardware. So this is how you can strategically define the test cases and apply it for a quality process. So with this, we are coming up with a automated solution, or we can come to an automated solution that combining the agile methodology and the v-cycle development strategy from the code centric testing towards the functional testing from right from the development team. So here we are also enabling the developer to get the validation environment from the developing stage. Right from the prototyping, you can have the validation environment, go for a rigorous testing at each level, and come to a come up with a quality product at the end. So yeah, then we have come to know like how we have come for SIL, why the SIL was adapted, why was the push, everything we have understood. And now we will see what are the roles and definitions of the SIL and HIL use cases. So with the software in loop, we are, as the slide itself explains or the name itself explains, software, we are keeping the algorithm or embedded software which is running on your host PC, which is also interacting with your simulated plant model. What does this typically do? This typically enables us to debug the at the early testing and debugs on the function with the software integration level. Like for example, sensor fusion, control, speed control, perception, etc. To test the application or software integration before moving to the prototyping hardware, to establish the continuous testing by running the rigorous test after each code change, to make the simulation environment available for the development for fast fault analysis. And this enables the left shift of the validation and which saves the cost. Whereas when we come to the hardware in loop, it is with the real hardware, real embedded hardware, and the real time simulation. Where in the software, it is the soft real time or the PC based simulation, where the hardware in loop could be used to enable that testing with the real controller hardware, to test the hardware software integration before moving to a prototyping vehicle, ensure the deterministic real time behavior for all the single ECUs, including the communication. Here, you can also verify the electrical failures and also can be integrated with the continuous testing. So now that we have know the roles and definitions, how we are categorizing it, how we are framing it, how we will decide where we can start it from. So when we go for, we can segregate the total framework in two criterias or two methods. Like one is based on the criteria where we are where the criteria for preferring SIL or HIL would be fidelity, volume, availability, and cost. The other would be the function algorithms or the ECU function category that is coming in. So criteria would be when we go for criteria, if you have the software logics available with you, you can prefer SIL and go with the software in loop simulation. When the fidelity for you is the hardware effects or timings, you can prefer HIL and go for hardware in loop simulation. When the test or when the criteria would be the speed or volume, the number of test cases that you have to run, then you can, if you want to exclusively test, run a number of test cases with the higher iterations, then you prefer go for a software in loop, thoroughly test your application, then go for the hardware in loop simulation. When your preferences is like you want to have a lesser volume of test iteration, and because the hardware, like the cost per simulation with the hardware is relatively high, then you can go with the then the HIL would be preferred. If you have hardware, prototyping hardware, you can go with the HIL. If you are do not have the hardware with you, but only the functionality, but you want to start the early testing, go for the pre-hardware. So when you go with the SIL is like when you are having like low cost and you want to detect the issues at the earliest point, you can go for SIL. And when you have like high fidelity and it is okay or manageable to find the risk at the later stage, the cost and the other criteria which comes in is manageable, then you can prefer going for HIL. When it comes to the functional categories, you can decide on like on the algorithm you have. If you have just, if your concentration or is to check the logic of your software, then it is best done in SIL than in HIL. If your concentration of testing is on application software component, then it is best in SIL. When you want to have a communication check with the protocols or stacks available, you can still go with the SIL. And if you want to do it for a physical bus conformance, and this is best done in HIL. When you take the timings and performance, whatever you do in the SIL is like the simulated or the scheduled time or a soft real time, we could say. But what we are doing it in HIL is like more the real time execution. If we consider it is for the safety or the compliances thing, what SIL covers best is the model coverage and the code coverage and a minimal of fault injection. But what HIL cover is like hardware faults, like the electrical faults and the other faults there. When you're going with the category of integration, software cross-functional along with the closed loop plant model, then best in SIL. And when you go for hardware IO along with the plant models, then it is best in HIL. So SIL doesn't replace HIL. Like what we have seen the differences where we have to use the SIL, where we have to use the HIL. So when we are introducing SIL or when we want to go for SIL, how it is complementing the HIL. So SIL always acts as a scout or qualifying software maturity before you go for the hardware allocation. So it always complements the HIL. So if you take the software correctness with the SIL, if you are able to detect the bugs at the earlier stage, then it reduces the debugging effort that you have to put on the hardware testing. If you take about the testing speed and the repeatability, still you can go for n number of test cases. You can fastly execute all the test cases. You can repeat the fault and check. This will release the HIL for the other test. So you only have to concentrate on hardware to software test, like how the hardware is integrating with the software. But the software test is already done. Only a minimal test are could be done on the HIL. When you go for functional verification, validate the individual software, you can complete it in SIL environment, and focus on the hill integration. Suppose like software on the system integration as well. In the SIL, if you can perform all the software functional test, here you are left with the hardware integration and timing test. How two hardware are integrating with each other and how best the timings are within them. If you want to go for model to code equivalence, the SIL plays a major role in checking all the model design, code compliances, and everything. And with this, while doing the HIL, you don't have to concentrate on the software behavior, because every checks on the software is done in HIL, so you don't have to put an extra effort in the HIL again to test all the software behavior. So if you can catch the risk at the earliest as possible, the cheaper it is to fix it. And this will minimize the cost that we put on hardware for all the retests. Resource efficiency, which enables the parallel software development. Here, since we are bringing the validation to the development environment, so we can parallelly develop the software and parallelly test the software. So this will help us to optimize the HIL test resources utilization. So this is how the HIL is complementing the SIL is complementing the HIL. With all this, how dSPACE can help you with it. We are saying that we are going with the agile methodology. You can go with the agile methodology for the development, for the validation. So DSpace has tool sets like target link, which can help you with the production code generation from the unit testing or the application testing, and for integration of the software component and integration software component integration and testing the individual software component. System desk and vios would play a major role, where system desk helps you to generate the virtual components for virtual controller part, and vios helps to simulate it. So when you have the hardware, you all know that the Scalexio is our major tool, which helps you in all the levels of validations when you have the hardware as a artifact to check. So VIOS plays another role, while we can also collaborate or co-simulate with the other environment with the COSIM interfaces. So basically, if we take the VIOS toolchain or the SIL platform for in the DSpace. So VIOS is the major platform. It enables us to take all the artifacts in different level. For like if it is in the modeling level, you can take the SIG files and go for the simulation as early as possible. If it is in the functional mockup unit artifacts, you can also take in. And if you want to integrate it and check with the bus simulation or the protocols, then bus simulation containers could also be taken. For the virtual artifact, for the levels of integrated software component, we can use system disk and go for testing. VIOS also enables us to co-simulate with the Scalexio platform when your system under test or DUTs, both software and hardware, also enables the smooth transition from SIL to HIL. The rest of the tool chain, like the experimentation, the testing, the parameterization, visualization software remains the same. So the control or the instrumentations that you have created for from the prototyping, in that case, from prototyping to the software in loop and to the hardware in loop, can be maintained same. So we could see there is a seamless reuse of data from mill to or from SIL to HIL. And this is how DSpace can come in and help you out. So with that, I would like to hand over the session to Lal, so we can walk you through or we can go for a demo session. Over to you, Lal.
Yeah. Thank you, Swati. Hello, everyone. Good afternoon. So, from whatever Swati has mentioned, that what DSpace offers, and then how we can do the HIL testing, how we can do the SIL related testing using DSpace tools. So, I just wanted to showcase how we could do SIL testing, and I will provide an use case where we have established the SIL testing for battery management system. So I'll take you through those. Yeah. So before that, diving in depth, I wanted to give you an overview of a battery management system. So battery management system, it always have the measure of the voltage, temperature on the cell level and the stack level, and then it does the overall current measurement, thermal management, and then the safety critical things, and then the operations of the relays, etc. It is taken care. And then the BMC with all of the data provided before. With that, the SOC, SOH, the state of charge, state of health, and then the monitoring of the insulation resistance, and etc. There are multiple things which the BMC takes care of. And then we have CSCs. So CSCs are cell monitoring circuits or cell monitoring modules. So which has an task of measuring the voltages at each and every individual cell level, and then the temperature measurement, and then to make sure the balancing is happening, active or passive cell balancing. So out of this, you can see this is the image of the battery management controller, where this is the BMC, where the software or the entire functionalities are being taken care of. And then we have the CSCs, which is integrated with the cells, and then to check the voltages, to monitor the voltages, monitor the temperature, etc. Is used. And then the BMC has direct control of all the current voltage and safety relays. So this is an overview. So this, I think many of them are from different background. So I just wanted to showcase BMC in specific. The reason, because BMS is very safety critical, and then it has so many sensors, so many relays, and then so much time critical stuffs in this. So if it could be done for BMS, it could be done for other system also. This is what we want to showcase over here. Okay, so I will show you the HIL testing part. So BMS validation using dSPACE system for HIL. This is already established. This is well in place in the industry for so long. And then I just wanted to showcase you this. So here in this, if you can see, the BMC, the BMS is under test over here, and then we do have CSC is also under test. So this is called a mixed level of testing, where mixed level testing means it is partially the hardwares you have, those are real, partially it is within a simulated environment on the HIL. Okay, so you can see over here. So this is how in HIL this would look like, the BMS when you integrate and when you want to test it. So what happens when you move on to a SIL environment? Okay, so this is the SIL environment where entire your BMC, your CSCs, your cells, voltage sensors, current sensors, everything is being virtualized, and then you can test it. Okay, so here we do have now the major protocols of of CAN, ISO, SPI being available, and then the other major protocols are under development part, and then this is this would be coming in upcoming dSPACE releases. Okay, so now I have shown you what we do have for the VIOS, virtual ECU. But the major question comes as like, how do you create it? What is it from different OEMs, different tier ones? How do you create a virtual ECU? So for that part, if you see, we do what we would require is only the inputs from the tier one and OEMs, that the partially or fully created software, the BSW, ASW, MCAL layer. So if we have all of this, this is the only input what we will require from you. Later, whatever is required for example, for BMS validation. So for BMS validation, the system under test would be the BMS. Along with that, if you want to validate other environments, so how do you integrate your charging system, and if you want to check how is the battery being charged, how is the motor been running, how is the battery connected to the load, how do you do that? So that is done with the dSPACE ASM models. We do provide the ASM models for that. It is already available. And then how do you test it? So the testing is done basically with dSPACE tools, control desk, automation desk, and Synect. So this is done through this part. So if you want to integrate something on the, if you want to virtualize, if you want to do the SIL related part, then this is the only system what is required, and then dSPACE provide some customizations, and then we do support in creation of the VCU also. Okay. Going further, so this is something which would look like once your BMS virtual ECU is being created. So here we do have your CSC. So as mentioned earlier, we do have the AD BMS 6380 being implemented, and then implementation of other protocols could be possible. And then the BMC, CSCs, and transceivers are all implemented in one virtual ECU. Okay. Next, this is the technical setup. So this would be mostly from the developer side, where you will have all the application layer, service layer, ECU abstraction layer, MCAL layer, your hardware emulation, CSC emulation, SP emulations, and all the drivers. So all this could be integrated in the virtual ECU. So there are different levels of virtual ECU. So that that also according to the maturity of the software or maturity of the hardwares and other layers, you can build it. Okay. You can create the virtual ECU. If you want to test it partially also, that also could be done. So all together, we have the virtual ECU. And then I wanted to stress upon what could be, so taking BMS as an use case, I wanted to stress upon what could be done on the SIL and what could be done on the HIL. So there are, so as Swati mentioned earlier, there are some advantages when you do with the SIL, there are some advantages when where you have it in HIL, and there are some test cases solely it can be done only on SIL. There are some test cases solely which can be done only on HIL. So I wanted to stress on that. So if you want to select SIL for your validation, then it could be like, for example, in BMS, if some of your functions, if you want to validate only the state of charge functionality or the state of health functionality, current limits or battery resistance, only if you have only 3 or 4 of it developed. So if, for example, if you have 10 functions, out of which 3 or 4 only you do have, and then you do not have to wait for the other 5 functionality to be developed, you can still validate partially also. Okay. Then this would enable early level of testing, because this will reduce ultimately your development life cycle. You do not have to wait for your entire hardware to be ready, software to be ready, entire patch to be ready, and then you have to test it. So you can still validate it very early on the software integration level. And then you can also check the software integration before moving to the prototype hardware. Might be you might not have an hardware to flash the software and test, but still if you want to do, then you can. Okay, then if the hardware is not available, then if you want to test a safety critical system, because for BMS and all, there might be safety critical system, you might flash the software on the hardware, and then might be you find some issue. The battery might get catch fire or something. Hazardous things could happen. So instead of taking that risk, you initially do your test on SIL. If it is passed, then you move it on the hardware. So this is some methods you can follow over here. And then to make the simulation environment available for function development. So the advantage is that, so this will not be restricted only to the testing team. So even the function development teams, the team who develops the software, they can also test it. So it is like before coming to the tester only, they could do the validation and then get it back. Okay. So next, I wanted to if you have any other points, if you have it still a doubt, okay, is still better or HIL better? We are definitely here to help you out on this. Okay, and then if you want to select HIL, then this could be the reason. So if you want to check the software and the hardware, how the integration goes on, if you want to test it, then this is the way. HIL is the way. To check the communication between the ECUs, to test the electrical faults. How so? For example, if you want to short circuit something and then check how the software responds, how the hardware responds, what are the issues that are happening in behind. If you want to check the robustness of the system, then HIL is the okay. Then to check the isolation faults, internal resistance, insulation faults, etc. And then to check the integrity of the ECUs, the zone controllers, or the emulated cells, sensors, loads, etc., then HIL is the way. Okay, so what I wanted to emphasize is then is it double efforts? So for example, you have a team who works on SIL, okay, and then what happens with the SIL testing, with the test cases that you have already generated, you have put a lot of efforts on testing or creating test cases for the SIL. So what you do with that? So it's never something which goes into scrap. So the advantage of the dSPACE system is that we can, with minimal changes, you can adapt these test cases on the HIL. So later point also, so if you develop some test cases on the SIL, the same could be taken over and then it could be tested on the HIL also. Okay, so with this, I'm ending my presentation, and then I wanted to show you what so we have already integrated the virtual ECU for battery management system. So there is a demo which I have which has been created, and then I wanted to showcase you how it looked like. I wanted to just show you the user interface, and then I think we are running out of time, so I will just show you a report of how the tests were conducted and how effective it is. Okay, so yeah, so this is the control desk tool which is used for the instrumentation purpose, and then here you can yeah, you can see all the layouts of the battery management system. So battery high voltage, all the loss calculation, entire circuits of the BMS, what is the state of charge, nominal cell voltage, current and voltage graphs, everything we do have. The pre-charge circuit, BMS main module 1, where you will have the each cells, how is the data of each cell, what is the value at any moment of time. So this is available in the control desk. And then we do have the automation desk tool, where there are some sample test cases which I have already run across. And then I wanted to showcase you the test which I have run. So this is for an example. This is for the under voltage test. So to check if the DC link, so this part. So if there is any reduction in the voltage, okay, if there is any reduction in voltage or it goes beyond some point, how is it captured, what is it happening, whether the test case is getting passed or failed, how do you validate it? So for example, over here you can see, I will go to the graph that will give you more this one. So from here I have started my test, where my SOC percentage was just about 20%. I started to discharge, and then once it reaches below 19.6, where it is approaching 19.5 percentage, I can see there is a fault being triggered. So from the ECU, so there is a DC link voltage. It goes beyond, and then an under voltage flag is being raised. So here I can see there is an under voltage fault being raised, And then you can see the upper relay, the relays, what is the status of the relays, whether it is getting opened, it is getting closed. So here you can see once that fault is triggered, you can see the relays getting open. Okay, so this is one sample test case, and then through this I wanted to share to you that it is possible for you to validate BMS and also other systems using dSPACE tools. Yeah, yeah. And with this, from my end, my presentation is over. I will hand over to Swati and Surya. Thank you, everyone.
Yeah. Yeah. Thank you, Lal. Yeah, I think this was an example that dSPACE provides the tool sets for even for all the other application. For example, here we have taken the BMS use case and we were able to perform both the SIL and HIL case. And if you are interested in having any of the demos, you can reach out to us for with respect to might be with respect to BMS alone, or with the other cases also you can reach out to us. And yeah, and as there is also one case like what Lal was explaining, there is a test results are matching in both the when we run the same test with respect to SIL and with respect to HIL, and we are finding the match here. So yeah, there is one more example from the global players like Stellantis, where they have also used the uh, SIL Hill platforms from dSPACE for their use case. So I'll just walk through what they have done. Like they have integrated SIL and Hill, and they have deployed dSPACE on the AWS cloud. For the SIL platform in AWS cloud, and for the SIL platform, they have used Vios, and for the Hill platform, they have used Scalexio. For the cloud platform, they have used AWS EC2, and for the ARM cloud platform, they have used AWS Graviton. So with this, Vios could be coupled with the AWS Graviton. As we explained earlier, like it is capable of co-simulating with that. And with this, what they were able to achieve, that they were able to achieve early testing, early debugging, and seamless integration between the SIL and HIL. And the other thing is that since all these were mounted on the cloud and the global collaboration was very much good. So according to them, they strategize their test cases like with this 80% of test could be done on cell and 10% on hill and 10% on vehicle in loop. So with this, according they have detected mostly like 80% of the software errors in the cell testing, and this have enabled them to like be the faster to the market, and they have cut down all the validation expenses that they were putting all these times. So other players who are using SIL toolchain, SIL toolchain is like from GM, Stellantis, Oshkosh, Toyota, and MAN. So these are some of the global players who are using SIL platform and various other tools from dSPACE for virtualization, for validation, and for testing as well. So yeah, that comes to end. And what are the key takeaways that we have from the webinar that we had? So if you are going with early validation, if you're starting with early validation, virtualize the ECUs, enable rapid and cost effective testing. This also reduces the burden on HIL by catching issues earlier. Use HIL for the real-time hardware where you are like hardware accurate validations are needed for the realistic performance, and you can ensure all the realistic performance in the HIL. Integrated approach gives the best results. So when you have both integrated and workflows are seamless, easy to switch between SIL and HIL, this gives an easy integration, and this will accelerate the development. So yeah, enabling this into a cloud platform gives you the global collaboration and the scalability. So SIL accelerates early development and minimize the HIL complexity. HIL ensures the final system integrity. So modern teams combine both for speed, quality, and cost efficiency. Yeah, and this comes to the end of the presentation,
And it's been great having you here. Thank you for the special thanks to Swati and Lal and Jane for putting this together. Swati and Lal for presenting the whole thing, and Jane for helping with the responses. Really appreciate all the support. And yep, thank you all. Have a wonderful evening ahead of you. And we look forward to hearing from you and working with all of you at some point. Take care. Bye.
thank you all. Bye bye.
Yeah.
dSPACE, your partner in simulation and validation.